All right, and one last thing that I wanted to do was one more example of calculating the root mean square velocity of a gas at a given temperature. This time going kind of to an extreme with xenon gas, which is a really large, heavy atom at 0 degrees Celsius, which is a pretty low temperature. So what would the root mean square velocity of xenon be at 0 degrees Celsius? Use the same equation that we used a couple of minutes ago for the nitrogen and hydrogen and carbon dioxide. Um, 0 degrees Celsius and temperature would be 273 Kelvin, of course. R, because we're talking about velocity, which has to do with energy, we need the energy version of R, which is 8.314 joules over moles kelvins. And the molar mass that's mm. It got kind of mangled. The molar mass of xenon is 131.3 grams per mole, but that needs to be in kilograms per mole. So that's 0.1313 kilograms per mole. And so we can put these into the equation where you have square root of 3 times 8.314 joules per mole Kelvin times 273 K all over 0.1313 kilograms per mole. And that's the square root of that. Okay, so we can start out with 3 times 8.314 times 273 divided by 0.1313, and you get this number right here. And then you raise that to the 0.5 power, or take the square root of it. It's the same thing either way. And we get 227.7, well, we're already over significant figures. So we'll just call it 228 meters per second. And if we compare this to what we got before, xenon is even heavier than carbon dioxide, and we're looking at it at a lower temperature than we did for the carbon dioxide, which was 21 degrees Celsius. So this should be a lower velocity. And you'll notice it is. We got 408 meters per second for the carbon dioxide at 21 degrees Celsius, and we got 228 for this. And so it checks out. 228 would be 228 is probably still probably around 400 miles per hour or so if we were to do the calculation. Okay, moving on. We come to the idea of mean free path and diffusion and effusion. Mean free path or MFP as it's sometimes called, is the average distance a particle of a gas can travel before colliding with something. Okay, so for example, for nitrogen at room temperature, the mean free path is about 310 molecular diameters. So a nitrogen molecule can travel about 300 times its own size before it hits something else, which is, pretty far actually. considering how fast they're moving and how many gas particles there are, to be far enough apart that they can travel 300 times their own size without hitting anything is pretty impressive. That would be like basically a golf ball traveling 40 feet before hitting anything else. And there are certain things that will affect the mean free path. For one thing, the mean free path decreases if pressure increases, because the particles would be closer together. And it works the other way around too. If the pressure is decreased, then the mean free path increases because the particles are further apart. Generally speaking, the temperature has no effect on mean free path though, because mean free path is a distance. If you raise the temperature, the particles will be moving around faster and it will take them less time to collide with something else, but it'll still be the same distance before they collide with something else. And for volume, if volume goes up without changing anything else, then mean free path would also go up because, well, I think increasing the volume without changing the, well, without changing the temperature wouldn't have any effect, but if you increase the volume without changing the number of molecules, then the molecules are going to be further apart, and that will increase the mean free path. They can go further before hitting anything else. If the volume is decreased, then the mean free path is also decreased. Because again, if you compress a gas without changing the number of molecules, then you're pushing the particles closer together. And that means that they will hit each other in less of a distance. Mean free path is related to the concept of diffusion. Diffusion is the spreading out of gas particles into another area due to a difference in concentration. So it's a spreading of gas particles due to a pressure gradient. And by pressure gradient, what we mean is that the gas will spread from an area of high partial pressure to an area of lower partial pressure. Now, remember, when I'm talking about partial pressures, I mean the partial pressure of that particular gas. So you're not necessarily talking about the total pressure here. If you have, say, an airtight room, and you have some carbon dioxide gas that's kind of segregated off in one corner, then that means that the partial pressure of carbon dioxide will be relatively high in that one corner where all the CO2 is. And the partial pressure of CO2 will be lower everywhere else in the room. Generally, what nature wants to do is spread things out as much as possible. Nature wants basically everything to be the same everywhere, as much disorder or randomness as possible. And so what's going to happen is that carbon dioxide is going to spread from the area of high concentration or high partial pressure for that particular gas into the areas where there's a lower concentration of that gas or a lower partial pressure of that gas until everything is even. Okay, so the ultimate goal would be an even distribution of the gases throughout the available space. And this goes back to the fact that gases mix homogeneously. And that, again, well, first of all, that means what that means is that if you release, say, a gas into another gas, if you have a container that contains gas A, and you release some gas B into it, gas B will immediately expand into the container and will mix evenly with gas A almost instantaneously, and you will have gas A and gas B everywhere throughout that container. And their concentrations will be the same all over that container. And that's what we mean by mixing homogeneously. And the reason that they mix homogeneously is because the particles are in constant motion, rapid motion. Not only that, but in random directions. So it's not like the particles that the new gas particles that you introduce into the container, they're not going to go just in one direction and off to one corner. They're going to spread everywhere because they're moving in random directions. And also because there are no intermolecular attractions or repulsions. Except for when they collide. And then they just bounce off of each other and go in a different direction. Okay. Heavier molecules will be slower to diffuse. And that just has to do with their average kinetic energy. So, they have lower average kinetic energy, so they're going to be moving slower. Smaller particles will have higher average kinetic energies, and they'll be moving faster, and so they'll spread around more quickly. And there's also effusion, which is a related concept, but not exactly the same. Okay, so effusion has to do with gas escaping from a container through a small pinhole. Whoops. Okay, so through a small hole, which we'll call a pinhole. The heavier molecules Whoops. And the heavier molecules in a sample, if you have this like a mixture of gases, the heavier molecules will effuse more slowly because they have a shorter mean free path. And also they're moving more slowly. And the effusion rate will be proportional to 1 over the square root of the molar mass. And from this, we get what's called Graham's law, where you can compare the effusion rate of two different gases. So you can compare the effusion rate of gas A to the effusion rate of gas B. And that is, since the effusion rate is proportional to 1 over the molar mass, that's actually going to be equal to the square root of the molar mass of gas B over the molar mass of gas A. So you switch the two gases around when you're taking the square root of their molar masses. And that is Graham's law for effusion. Okay, so we can have a look at finding the ratio of the effusion rates of hydrogen to krypton. Okay. So if we want to take the ratio of the effusion rate of hydrogen to the effusion rate of krypton, that's just going to be the square root of the molar mass of krypton over the molar mass of hydrogen. In this context, the molar mass can be in grams per mole, or you can change it to kilograms per mole if you want to, because the ratio of the two numbers will be the same either way. So we'll just leave it in grams per mole. Because you see, the units are going to cancel out anyway. If you changed these to, what do I want to say? If you change these to kilograms per mole, 83.8 would be 0.0838, and 2.02 would be 0.00202. But that ratio would come out to be the same as the ratio of these two numbers. And when you take the ratio and then take the square root of it, you get 2.04. So hydrogen effuses at about twice the rate of krypton. You'll notice that there are no units because the units disappeared because grams per mole divided by grams per mole cancels out. So there are no units. It's just a number. Okay, so that's kind of a quick review of effusion. Something that we really need to be sure to cover before the end of the chapter is the idea of reality. Yeah, reality, what a concept. We have to cover real gases. And I mentioned that under most circumstances that we encounter in general chemistry anyway, the behavior of real gases will conform to the ideal gas law, or to the kinetic molecular theory, or will at least be close enough that there won't be a lot of error. But we should still be aware of the ways in which real gases deviate from ideal behavior. Just kind of so that we can recognize it when it happens and so that we can be aware of how to correct for real behavior. And so, as I've mentioned, under certain circumstances, real gases can deviate from ideal behavior. There are certain circumstances under which this deviation can be significant. And deviations from ideality or ideal behavior are especially pronounced at low temperatures and or high pressures. Basically, it's the kind of things that force the molecules together for longer periods of time. So low temperature, because it slows the molecules down so that when they collide with each other, maybe they don't bounce off each other immediately. And that can allow certain intermolecular attractions to come to the fore and exert themselves, which can cause the molecules to start sticking together a little bit, which is a deviation from ideal behavior. Other things like high pressure, because high pressure forces the particles closer together. That again can allow them to be near each other long enough so that intermolecular attractions can become noticeable and start exerting themselves. So those are the circumstances where the deviations from ideal behavior are the worst. There can be deviations under other conditions. And of course, what exactly is low temperature and what exactly is high pressure, that can actually vary somewhat from one gas to another. So the definition of how low does the temperature have to be or how high does the pressure have to be can change somewhat depending on what gas you're dealing with. Okay, so under conditions of low temperature and or high pressure, real gases can deviate sometimes significantly from ideal behavior. Real gases' behavior would be closest to ideal under conditions of high temperature and low pressure. And again, exactly how high the temperature has to be or how high or how low the pressure has to be for a gas to behave ideally will depend on what the gas is. But as it turns out, most gases are close enough in the vicinity of room temperature and normal atmospheric pressure. And so, by that I mean, around 25 degrees Celsius and 1 atmosphere. Generally, with regards to pressure, I'm trying to remember, but I think that for most gases, the pressure has to get up around 10 times the normal atmospheric pressure before they really start deviating significantly from ideal behavior. And for most gases, the temperature has to get low enough that they're on the verge of condensing to a gas. So essentially, the melting point or the condensation point for most gases would be around the temperature where they start deviating from ideal behavior. Okay, some gases will actually deviate from the standard molar volume at STP, that is standard temperature and pressure, but not by very much. They give a comparison of the standard molar volume for various gases at standard temperature and pressure. And most of them are right around 22.4. They give this in the book. But there are a couple that are like 22.3 and one that's maybe as low as 22.1. Still pretty close though. Okay, the reasons for deviation from ideal behavior have to do with two things: the volume of the particles themselves and the fact that they actually can be attracted to each other under the right circumstances. Okay, the kinetic molecular theory says that gas particles have infinitely small volume compared to the distance between them. In other words, what that means is they have no volume. And of course, we know that that's not true because anything that exists physically has to have volume. So these gas particles might be really small, but they do have some volume. And this becomes significant, or rather the volume doesn't become any bigger than it normally is, but it becomes significant as the particles are forced together at high pressures. Okay, so at higher pressures, you've got the empty space between the particles being compressed, and the particles are being pushed closer and closer together. And the volume of the gas should be going down at a certain rate as the pressure goes up. But you find you get to a certain point where the particles are on the verge of bumping right up against one another, and you have a harder and harder time compressing the gas, even though the kinetic molecular theory says that you should be able to compress the volume of the gas right down to zero without any resistance. But you do start facing resistance. And so the high pressure forces particles together. And that means that the volume of the particles becomes a significant percentage of the overall volume. Normally at like standard temperature and pressure, the volume of the gas particles themselves make up a tiny percentage of the overall volume of the gas. But if you're going to start compressing the gases and pushing the particles closer to each other, then you're going to get a situation where the gas particles themselves take up a significant amount of space compared to the overall volume of the gas. And so it turns out that the volume of real gas will be slightly greater than what's predicted by the ideal gas law. As the pressure increases. And there's a diagram on page 214 that you can look at that shows the deviation. Actually, in practice, you'll notice that even once the gas really starts deviating from the ideal gas law, even then, it's not that far off. But it's far enough off that it could cause significant errors. But in chemistry, by significant error, we usually mean anything more than about 5% is usually considered significant error. So, in sort of the everyday way of viewing things, 10% doesn't seem like that big an error, but in chemistry it would be. So that actually is considered a significant deviation. And this is due to the volume occupied by the particles themselves. And that's actually another reason when you think about it, well, we're dealing with pressures here, but also according to Charles' law, as you lower the temperature, the volume of a gas should be getting smaller and smaller. And when you get to absolute zero, the gas should have zero volume. And obviously that can't happen because the particles themselves take up a certain amount of space. And so that's actually another reason that we'll probably never actually be able to reach absolute zero, because whatever particles you're cooling down have a certain volume. They cannot get down to zero volume. There was a scientist by the name of Johannes van der Waals, or van der Waals, if you prefer to pronounce it that way, who studied gases and their behavior. And he came up with a lot of the information on intermolecular attractions, which we'll be dealing with in a moment. But he also came up with the equations that correct for non-ideal behavior among gases. And so van der Waals modified the ideal gas law to take account of the volumes of the actual molecules. And so he said volume is equal to nRT over P, that's the ideal gas law, plus this extra factor, which is NB. Where N is the number of moles of gas, and B is a constant that depends on the identity of the gas. The units would be liters per mole, and values for B can be found on page 215. So these are the van der Waals constants. There are two of them. One of them will be, oops, sorry, A will be covered in the next section, and B is the one we're talking about now. So B is for various gases. Every gas has its own value for B, A and B, and you can look them up. This is a table of some of the values for some of the more common gases. And we'll get back to A in a little while. The equation can be written like this, but it's actually also often written as V minus NB, because this is the modification for the volume, equals nRT over P. And the second form actually conforms more exactly to the way that the ideal gas law is usually written, which is, V equals nRT over P. Well, that would be the ideal volume equals nRT over P. And if you rearrange the van der Waals equation this way, you get the real volume equals nRT over P, because the real volume is V minus NB. So this is the volume of the gas, subtracting out the volume of the particles themselves. Okay, so that's what that is. That's the correction to the ideal gas law. Okay, well, we're well over 30 minutes for this segment, so I'm going to go on to part C, and where we'll talk about intermolecular forces.